Are you ready to learn even more identity equations? At this point, you may be wondering, how many identities are there? While it's true that there are more identities out there than we can memorize, we're actually learning the most common and useful identities. In 3.5, we'll add the double angle and half angle identities. Let's begin in 3.5.1 with the double angle identities. Now, a double angle is exactly that. If you notice in the argument, we are multiplying the angle by 2. The double angle identity for sine is sine of 2x equals 2 times sine of x times cosine of x. Notice in this formula that the angle on this side of the identity equation is half of this angle. To see where this identity comes from, we're going to build it on one that we already know, that is sine of a sum. So first notice that sine of 2x can be expressed as sine of x plus x. Then we can expand this using our sine of a sum formula. That is sine of the first angle, x, times cosine of the second angle, plus cosine of the first angle times sine of the second angle. Now, ultimately, these two terms are like terms. Remember, multiplication is commutative, so I could reverse the order of these factors, and then both of those terms would look identical. So because they're like terms, we can combine them as 2 times sine of x times cosine of x. This is an important proof to remember because if you're ever in the situation where you need that double angle identity and you can't quite remember what it is, you could always derive it yourself using this process. 1. Let's examine the double angle identity for tangent. Tangent of 2x can be written as 2 tangent of x divided by 1 minus tangent squared of x. Again, notice the relationship between the arguments. Over here, the argument is x. Over here, we have double that angle, 2x. Now, we can derive this formula using a method similar to what we did for sine of 2x. Tangent of 2x can be written as tangent of a sum, that is tangent of x plus x. So we're building this new double angle tangent identity on an identity that we already know and have proved before. Tangent of a sum can be expanded as tangent of the first angle, x, plus tangent of the second angle, x, divided by 1 minus the product of those two tangents, that is tangent of x times tangent of x. As a quick reminder, in the tangent of a sum identity, the sign that's between the original arguments matches this sign right here, and then we change the sign in the denominator. Getting back to our proof, we can simplify the numerator as 2 tangent of x, and in the denominator, we can express that as 1 minus tangent squared of x. So that verifies the double angle identity for tangent. Again, remember this process. If you were to forget what was the sign, what were the details of that identity, you could certainly verify it by hand. Now for cosine, we have a lot of options. Bad news is we get 3 double angle identities for cosine. However, they are all related. The first useful formula for cosine of 2x is expressed as cosine squared of x minus sine squared of x. Now, this is not to be confused with the Pythagorean identity. That is sine squared of x plus cosine squared of x equals 1. So pay close attention to the details of certain expressions. If you see sine squared of x plus cosine squared of x, then we can replace that with 1. But if we see the difference between the squares, cosine squared of x minus sine squared of x, then that gives us our double angle identity. A good way to remember this formula is to remember the proof or the derivation of this formula. So let's rewrite cosine of 2x as cosine of a sum, cosine of x plus x. Then we can expand that using our cosine of a sum formula. Recall, we take cosine of the first angle times cosine of the second angle. We're going to change the sign here to get minus sine of x times sine of x. Then you can see very quickly when we simplify, this can be written as cosine squared of x minus sine squared of x. So again, remember this process here. In case you happen to forget this identity, you can certainly derive it by hand. Now, because we have these Pythagorean terms, cosine squared and sine squared, we can express the double angle identity for cosine in different ways. Cosine of 2x can also be written as 2 cosine squared of x minus 1. To see where this form comes from, I'm going to begin with our first formula. That is, cosine of 2x is equal to cosine squared of x minus sine squared of x. Then, rearranging our Pythagorean identity, we can see that sine squared of x is also equal to 1 minus cosine squared of x. So I can replace this sine squared of x with this equivalent expression. This gives us cosine squared of x minus, now I'm replacing sine squared with more than one term, so I'm going to go ahead and put this in brackets, 1 minus cosine squared of x. Let's go ahead and complete the distributive property here and write this as minus 1 plus cosine squared of x. Then you can see we've got a couple of like terms here, which could be simplified as 2 cosine squared of x minus 1. So that verifies the second form of our double angle identity. Let's consider one more form of cosine of 2x. This can also be written as 1 minus 2 sine squared of x. Now to derive this one, I'm just going to work from the work that we have here where we left off. We can replace cosine squared of x with 1 minus sine squared of x. Okay, now where did that come from? If we go back up to our Pythagorean identity and we solve this for cosine squared of x, I'll do it over here, you can see cosine squared of x is 1 minus sine squared of x. So using that Pythagorean identity in its various forms, we can see how we're replacing cosine squared of x with 1 minus sine squared of x. Okay, let's distribute. This would be 2 minus 2 sine squared of x minus 1. If we combine like terms here, 2 minus 1 gives us 1, and we have 1 minus 2 sine squared of x. So you can see cosine of 2x is equivalent to this expression as well as this expression. So the three different double angle identities for cosine are useful in different settings, and they're all related. So it's really helpful to memorize these identities together and alongside that Pythagorean identity so that you can learn the difference. Let's see how these identities might help us to simplify some expressions. On example 1, it says use double angle identities to simplify each expression. Example A is 2 times sine of 12 degrees cosine of 12 degrees. Recall that sine of 2x is equal to 2 times sine of x cosine of x. The form of the example matches the form of the expansion of our double angle identity for sine. So we can condense it into sine of 2 times x. Notice these arguments are both 12. If x is 12, then 2x is going to be 24. So we can rewrite this expression as sine of 24 degrees. Notice you could certainly check that with your calculator. First, I'm going to make sure I'm in degree mode, and then I'm going to type in our original problem. That's 2 sine of 12 degrees times cosine of 12 degrees. And observe the output. And then I'm going to type in our simplification, sine of 24. Notice we get exactly the same output. This is an irrational number, and it's not in terms of a common angle on the unit circle, so sine of 24 degrees is a sufficient simplification. Notice the pattern of example B. We have tangent of 15 degrees over 1 minus tangent squared of 15 degrees. Hopefully this reminds you of our new double angle identity for tangent, which is tangent of 2x equals 2 tangent of x divided by 1 minus tangent squared of x. Now the given expression is really close to the right side of our identity, But did you notice it's missing a 2? So we could say that tangent of 15 degrees over 1 minus tangent squared of 15 degrees is 1/2 tangent of 2 times 15 degrees, or 30 degrees. Now, where did this 1/2 come from? Well, notice if I multiply both sides of this identity by 1/2, it's going to cancel the 2 from the numerator in the identity, so that now this side matches this pattern exactly. So to replace it with something equivalent, we definitely have to include that coefficient 1/2. Unlike the previous example, 30 degrees is a unit circle angle, so we can go ahead and evaluate tangent of 30 degrees. Recall that tangent of 30 degrees is the square root of 3 over 3. Simplifying here, we end up with square root of 3 over 6. Now that one's definitely worth checking on our calculator. Now I am already in radian mode, so I'm in degree mode, so I'm going to go ahead and type in our original problem. That is tangent of 15 degrees divided by, now we need to be careful here when we enter the denominator, because there's an operation in the denominator, we need to get it in a set of parentheses. So I'm going to open parentheses, 1 minus tangent of 15, and then I can simply square it by typing the x squared button. That doesn't square the argument, that in fact squares the entire tangent function. And then we'll type in our answer, square root of 3 divided by 6, and we'll compare decimal values. And because they match exactly, we know that we have evaluated it correctly. Remember, our goal is to express this exactly, but we can use the calculator approximation to check. These types of problems are all about pattern recognition. So on example C, when I see 2 cosine squared of something minus 1, it reminds me of one of the forms of our double angle identity for cosine. So specifically, cosine of 2x, we can see it right there, can be written as 2 cosine squared of x minus 1. But do notice this argument is a little bit complicated. Let's see what we can do about simplifying that argument. So for 2 cosine squared of pi over 5 minus pi over 2, because the argument involves a pi over 2, it's reminding me of a cofunction identity. But in the cofunction identities, the pi over 2 is always first. So I really need to switch these two terms around. But if I do that, I'm going to also have to factor out a -1. So let's write this as 2 cosine squared of, I'm going to factor out a -1, and write it as pi over 2 minus pi over 5. And then, of course, we have our -1 out here. Now, recall when you have a negative argument for cosine, we can simplify that with an even identity. Now, I want to be really clear the order of operations here. So what I'm going to do is show you that the cosine squared really means cosine, the entire cosine function squared, right? So I can think of that square as being on the outside of the cosine function. Remember, we write it between the cosine and the argument for shorthand notation or efficiency. But now I can see I can replace cosine of a negative angle with cosine of the original angle, pi over 2 minus pi over 5. Because cosine is even, okay? Then we can see cosine of pi over 2 minus pi over 5 can be replaced with its cofunction. And we can write that sine of pi over 5. Now this whole thing is needing to be squared, but I'm going to go ahead and transfer it back to the shorthand notation right here, 2 sine squared of pi over 5 minus 1. Now, our original diagnosis of the double angle identity pattern looks like it's not going to fit our new simplified form. We're going to need this form right here. 1 minus 2 sine squared of x is equal to cosine of 2x. And we almost have that here, but the terms are reversed. But I am out of room, and I bet you are too. So I'm going to borrow some space over here. And our original problem, 2 cosine squared of pi over 5 minus pi over 2 minus 1. we have simplified to this point right here. 2 sine squared of pi over 5 minus 1. Now I'm going to factor a negative 1 out of those two terms, and I'm going to reverse them at the same time. So that can be written as negative quantity 1 minus 2 sine squared of pi over 5. Finally, it matches our double angle identity for cosine. So this could be written as negative cosine of 2 times that angle, or 2 pi over 5. Now that was a lot of steps. We used cofunction identities, we used double angle identities, so that one is definitely a good candidate to check. Now this problem happens to be in radians, so let's go ahead and switch back to radian mode. And I'm going to type in the original problem. The original problem, over here to the right, example C, is 2 cosine of pi over 5 minus pi over 2. Don't forget that cosine was squared, and then we subtract 1. We're going to compare that to our answer, negative cosine of 2 pi over 5. And we obtain exactly the same decimal. So we can be confident that negative cosine of 2 pi over 5 is the correct answer. With the recognition of these new double angle identities, we now have the potential to recognize other relationships. So on example 2, we're going to use our new formulas to verify the following identities. Example A is cosine to the 4th of s minus sine to the 4th of s equals cosine of 2s. So this is interesting. It's another double angle identity for cosine. Let's start with the left side. There's a lot of potential for simplification over here on the left side. Notice on the left side we have the difference of two squares. So we can factor it as such. We'll take the square root of the first term, cosine squared of s, plus the square root of the second term, sine squared of s, times the same thing, same two terms with a different sign in between. Cosine squared of s minus sine squared of s. Notice we're just factoring the difference of two squares, a squared minus b squared, using the pattern a plus b times a minus b. Now, cosine squared plus sine squared is equivalent to 1 according to our Pythagorean identity. So I can replace that with 1, or we can just ignore it there. And the only thing that's going to be left, I'm going to make a note that's 1, is the other factor, cosine squared of s minus sine squared of s. And that we've already recognized previously in this lesson is equivalent to cosine of 2s. So that one was a very easy identity to verify. Let's try another one. Example B, we have sine of 4t over 4 equals cosine cubed of t times sine of t minus sine cubed of t cosine of t. I'm going to begin with the expression on the left side. Remember, you have a choice. You can begin either way. You just have to find the path to the other side. I'm going to expand the numerator sine of 4t using the double angle identity for sine. This can be written as 2 sine of half that original argument, in this case it would be 2t, times cosine of the same thing, 2t. And this is all divided by 4. Now at this point I can recognize a common factor. 2 cancels into that 4 2 times. Now let's replace the sine of 2t here with yet another expansion of our double angle identity for sine. That can be written as 2 sine of 1t, or just t, times cosine of t. Now, as far as cosine of 2t, we have 3 different choices, but notice if we use the first formula for the double angle identity, we'll be able to generate this right side. So I'm going to rewrite that cosine of 2t as cosine squared of t minus sine squared of t. And don't forget, this was all divided by 2, but not for long. These 2's will definitely cancel. Now we can use the distributive property and take this term and distribute it to the 2 terms of our bracketed element, and that's going to verify our identity. So we would end up with cosine cubed of t times sine of t when we distribute to the first term. And to our second term, we would have sine cubed of t times cosine of t. And that matches the right side exactly. So we have verified the identity. So in this section, we learned a lot of new formulas. You'll definitely want to add these all to your memory bank. Double angle identity for sine. We had one formula there. One formula for the double angle identity for tangent. And then we had 3 different formulas for the double angle identity for cosine of 2x. Those are important relationships to memorize and be able to recognize.